Hey guys, just to let you know, this lesson is in collaboration with Flip Academy, a free online platform for all of your GCSE, A-Level, IB and CBSE revision, out now on web at www.flip.academy, and also as an app for Apple, iOS and Android. It really is better than all the other GCSE platforms out there. It covers all the topics in great depth and has an app that you can download your courses on and use offline.
Hello and welcome back to Flip Academy. Today we're going to be looking at the circular measure topic of the CIE A Level Mathematics spec. So today this is all going to be about using radians. So the first question is, what is a radian? Well, a radian is just another unit for angles. That's all it is really. And what it does is it actually allows us to simplify a few of the equations that we have to use. So for example, you know how when you wanted to work out the area of maybe a certain sector, for example, you'd have to use that theta over 360 times pi r squared. Well, with radians you can just use now pi r squared and then times it by theta. So it makes things slightly easier for you. It's just r squared theta instead. And you have to be able to use these interchangeably with degrees. Okay, so what might be useful? So again, it's the exact same way as, like, you know how when we have, for example, distance, we have miles, we have kilometers, we have meters, etc. This is all that is, okay? It's just another unit. So if you want to go from degrees to radians, and converting does come up occasionally, all you do is you multiply by pi divided by 180. And therefore, if you were to go back, all you need to do is divide by pi over 180. Now, just because I know that some people might mention this, dividing by pi over 180 is the exact same as timesing by 180 over pi. Personally, I prefer to just remember pi over 180 because it's the same for both. So times to go degrees to radians, radians to degrees, you divide. But this is pretty much all you need to know. However, there is one other thing. I'm assuming that you have a fairly standard calculator, scientific calculator, and what you might be able to see is, if I make this a little bit bigger for you, you might be able to see that there is a capital D here. That is because we are in degrees mode. So why is this important? Well, we're going to start using the sine, cos and tan functions, right? Because we're dealing with angles, we're going to be using sine, cos and tan. Now, here's a really, really important thing. Whenever you're using sine, cos or tan, from now on, you need to check if you're in degrees or radians mode. And the reason for this is, let's say we have sine of 2 radians. That gives me this. That's not correct. This is sine of 2 degrees. So, to show you how to do this, all you need to do in order to kind of go and find where you need to change this, and again, if you're using this calculator, it'd be like this, but every scientific calculator will have this option. You press Shift, menu setup, click on angle unit, and you're going to press 2 for radians. So I'm actually going to set this right now, and as you can see, there's a capital R now. Okay, so now, from this moment, this day forward, this moment forward, every single time you use sine, cos and tan, and it only affects sine, cos and tan, don't worry about anything else, you need to check if there is a degrees, so a capital D, or a capital R. Okay? A lot of students, and it will happen to you once or twice, I guarantee it, will forget to check, and what they'll do is they'll take sine of a radian, but then they'll be in degrees mode and they'll get the wrong answer. It's common, it happens, it's fine. But it shouldn't happen in your exam, okay? So again, from this point onwards, please check if you're doing in radians or degrees. So for this video, obviously I can keep it in radians mode, but keep in mind, in your actual exam, they're going to change. They might say, oh, it's 30 degrees in this question, so find a side, so you need to use sine 30 or something. But then the next question, it might be an area of a sector where the angle's in radians, right? And again, vice versa, if they're saying find the angle in radians, you need to make sure you're in R, radians mode, and if you're in degrees mode, okay? So, that's what you really need to know about radians, and you should be able to kind of convert between them, and honestly that's probably the easiest part of this video. The rest of these questions is somewhat tricky. So let's get started, shall we? So, what we have first is we have to use the formula S equals R theta. So what this is it's the length of an arc. And what this one is it's the area of a sector. Now, again, you may remember slightly different formulas for the length of an arc. So what you might be remembering is you take theta over 360 and then times it by 2 pi r, right? Well, the key thing here is that theta must be in radians. So you can always use these formulas, 100%, right? Because you can convert from degrees to radians. So it doesn't actually matter in that sense, but for these formulas to work, theta has to be in radians. So either convert to radians or use it if it's in radians. Okay? So that's something you have to keep in mind. And please do. So let's get started with one of the questions. This is from the June 2018, paper 1. So the diagram shows a circle with centre O and radius r. The points A, B lie on the circle, and AT is a tangent to the circle. Angle AOB equals theta radians, and OBT is a straight line. Express the area of the shaded region in terms of r and theta. So what I like to do is think about this, think about it in my brain instead of before I do some maths. So for the shaded region, what we're going to do is we're going to take the area of the triangle, right, and we're going to subtract the area of the sector. Okay, and so in general that's just going to be half base times height minus, and again we're using this because this is in radians, we're going to use half r squared theta, right? So that's what it's going to look like in general. We just need to find out what all of these things are. Well, actually the area of a sector is done. Theta is theta, r is r, so we're fine. So what we need to do is, what don't we have for the triangle? Well, we have the height, you could call it, but we don't have the base. So how can I work out the base? Well, this is a right angled triangle. If you remember your circle theorems, the radius is always going to meet a tangent at 90 degrees. So we can use trigonometry, right? This is the opposite side, this is the adjacent side, this is the hypotenuse side. So what we can do is we can say that because we want the opposite and we have the adjacent, then we're going to have tan theta equals opposite over r. So the opposite side is just r tan theta. I promise I'll write this a bit neater. So now we have a half. Let's put the r first here. So r times r tan theta minus a half r squared theta. So what we can do here is make it a half r squared tan theta minus a half r squared theta. It doesn't say to simplify it at all, so we don't have to do anything, but you can factorise out the half r squared if you really want to, but you don't got to. So in the case where r is 3 and theta is 1.2, find the perimeter. Okay, so kind of duped us a bit. We're not going to be using this formula, but again, that's 3 marks, not too bad if you just think. Perimeter of the shaded region. Well, the shaded region is going to be this length, the opposite length, right? So let's actually write that out right now. Right, it's going to be r tan theta. Right, and what I like to do is above it, I'm going to write the letters. So I'm going to say that is AT. Yeah? So we have that length. Then we need to work out this length here, the length T to B or BT, whatever you want to call it. So, here's a cool fact. This length here, O to B, is going to be R, right? Because it's from the centre to the circumference as the radius, right? And what we can do is we can take this squared plus this squared and square root it in order to find out what the hypotenuse is. You can also use trigonometry. So we could say that this, for example, this is the hypotenuse side, so we can say that adjacent over hypotenuse, so we can say that cos theta is equal to r over h, if we wanted to. Up to you, really. But let's think. What would be easiest? Let's use trigonometry. So we have cos theta equals adjacent, which is r over, it's not bt, it's ot. So then ot is equal to r over cos theta. So bt is just going to equal r over cos theta minus r. So plus, and then if you want me to put it in brackets, don't really need to, r over cos theta minus r. So That's fine. And then we need to work out the arc length, which is r theta. We don't need to do anything with that. So plus r theta. Okay. And then we know that r is equal to 3 and theta equals 1.2. We can just substitute this all into a calculator. So again, there is trigonometry inside this, tan and cos. So check, I've got the r, not the d, and we're using radians, so that's correct. So now what we need to do is type it in. So we have 3 tan 1.2, whoops, plus bracket 3 over cos 1.2 minus 3 plus 3 times 1.2. So with radians, you don't tend to get a very nice answer, but that's totally fine. We get 16.6, I'm going to call it. Okay, and just so you're aware, what I'm going to do is I'm going to quickly change over to the other angle unit. I think this is it. Press equals again, I get a completely different answer. So it really, really, really does affect everything. If you're wondering what gradients are, they're a unit that are used in the military, so you probably won't need it, unless you're joining the military after sixth form. But yeah, you won't need that one. Okay, not bad. Now we have to go on to the next question, and it's pretty good. This is pretty okay. This isn't too bad. So we have a diagram shows a circle and then another circle. So there's a bit of an overlap. And these two are perpendicular to each other because they're chords, and this is like a radius or a diameter, so they would always meet at 90 degrees. And show that the radius of the larger circle is r root 2. So what I can do here is if I draw a line going from here to here, or here to here, either way, this length is also r. So in order to work out the length BC, which is the radius, I can just do square root r squared plus r squared. So that equals the square root of 2r squared, which is the same as doing r root 2. That's not too bad. Part B, though, is a 6 marker, which means it's probably going to be extraordinarily painful. Let's drag this back up here. Let's give us some room. And we have to find the area of the shaded region in terms of r. So again, just a bunch of algebra, which is going to be incredibly fun. There are so many different ways to do this question. Okay, so many different ways. You can work out, for example, the circle minusing this sector. You can work out the semicircle minus this segment, which is actually what I'm going to do. And yeah, you have various things that you can do. So what we're going to do first is we're going to work out the area of a sector. So if we work out the area of the sector, what we're going to have here, and by sector I mean the sector B, C, and this I'm going to call, this point here, let's call it F, right? B, C, F, D. We're going to work out this area of a sector here. Now if you notice, this is actually going to be a quarter of a circle. Okay? So a quarter of a circle. Now, one thing that you might notice if you did the if you change it from degrees to radians, 360 times pi over 180, the total angles in a circle is 360 degrees, which means it's in radians it's 2 pi. Okay? And that means 180 degrees is pi, that means 90 degrees is pi over 2. So in this case we're dealing with something that is 90 degrees because it's a quarter of a circle. That's why I wrote these little conversions down for you. So what we're going to do is, if we're working out the area of a sector, it's, if you remember, half r squared theta, so we have a half. Now r, the radius of this sector, is that length that we worked out here, so r root 2. Yeah. And that is squared times by pi over 2. So let's quickly expand this slightly. So this is going to be r squared times 2 pi over 2. So what we can do is we can actually get rid of one of the 2's. So we're left with a half pi r squared. Cool. The next thing I need to work out or I want to work out anyway, is it's going to be the triangle BCD. So that's going to be quite easy. It's just going to be standard half base times height. The base is r plus r, 2r, and the height is r. So 2r times r. So we can cancel out the 2 here and the 2 there. So we're just left with r squared. Now the reason why I did this is I want to work out the area of the segment, which is this little kind of slice here, which I'm going to call CFD. Okay. So the area of the segment CFD, let's call it, is going to be equal to the area of the sector minus the area of the triangle. So here's my general play, right? I'm going to work out the area of this big semicircle and subtract the little segment inside it. Now the segment is going to be this sector minus the triangle. So let's do that. We have half pi r squared minus r squared. Can't really do anything fancy yet, so I'm going to leave it as is. Now we're going to work out the area of the semicircle. Long-winded process, right? But again, big semicircle here. Minus this little, I always used to think of them as orange slices for some reason, but yeah, area of this segment here. And let's get through that. That is going to be a half pi r squared. You may ask why? Well, the area of a full circle is pi r squared, so a semicircle is just going to be half pi r squared, right? Because the radius is still r. So now we can work out the area of the shaded region, which is just going to be minusing all of that stuff from each other. So it's going to be the semicircle, which is a half pi r squared, minus the little segment, which I'm going to put the minus in. I'm going to put this whole thing in brackets because it's meant to be together. Now if you notice, this half pi r squared and that half pi r squared will cancel. Minus and a minus means the shaded area is just r squared, which is a really satisfying result. I hope you found that quite satisfying as well. But yeah, 6 marker, not that bad. Again, there are a few other ways that you can kind of work out those questions, but again, I don't find that to be too bad. But 6 marks, it's a long question, it's a big one. And again, it's all on algebra, which kind of sucks. Yeah, we're not going to stop. This is yet another pretty beefy, pretty tricky question. So we have this ice cream cone shape, and then also this semicircle, and there's stuff flying around, and everything's crazy. But here we can say that this is a chord, and this is a radius, right? So in other words, these are going to meet at 90 degrees and also bisect each other. So that is something that we can look at. And what we need to do for... So again, let's read through it. We have the length of the chord AB, 90 degrees. So since it bisects it, and again, this is at 90 degrees, this will be 6 centimetres, and this will also be 6 centimetres. Okay. The line OX passes through M, the midpoint of AB, and OX is perpendicular to AB. The shaded region is bounded by the chord AB and by the arc of a circle with centre X and radius XA. Okay, so they give us a lot of information. So if we write this out, we have this here is the radius of a big arc. And we need to show that the angle AXB, which is this big angle here, is 2.498 radians correct to 3 decimal places. Okay, let's start, shall we? So O to M is a value we want. Because basically what I want to do is this whole thing is 10, right? But I want to work out just this little bit over here. Just that little bit there. So this whole thing is 10. I need to work out what the length O to M is. So O to M is just going to be a simple case of Pythagoras, because this is a big right angled triangle. So square root 10 squared minus 6 squared. So that is the square root of 100 minus 36, which is the square root of 64, which is 8. So again, that means mx is going to be, or xm, whatever you want to call it, is equal to 2, right? And the way I got that is I did the full 10 from the radius minus 8. Okay? So we have that little 2, and we have a 6 here, and now we want to work out the angle. It's going to be quite simple. All we need to do is trigonometry. So we have 2 is here, this little bit there, and that's 6. We want to work out this angle, so that is the opposite and the adjacent, so we're looking at tan. Okay, so what we're looking at is tan AXM is equal to opposite, which was, I can't remember, 6 over 2. And again, remember, when we want the answer in radians, so we're going to get the answer in radians. The thing that we should note is, actually no, I'm going to do this first. And can you see that 6 over 2 is just 3, so I'm not going to bother writing the full thing. Tan inverse 3. 1.249 blah blah blah. There's a reason why I'm saying blah blah blah, so dot dot dot, because AXM is just this half of it, but again, we've actually bisected this thing because it's completely symmetrical. So if we want the full angle AXB, it's going to be twice that, right? Because it's the same on both sides. So AXB is equal to 2AXM. So if I just do 2 times answer, or answer times 2, 2.498 to 3 decimal places, which is exactly what they wanted. So let's write SF there. There we are. Okay, believe it or not, that's not even the hardest question. That's not even the hardest part of this. So, now we need to find the perimeter of the shaded region, which is basically a semicircle, right? So we already know the first part is going to be AB. So why don't we, make ourselves feel good and say that part of it is going to be 12 plus basically a big arc, right? So we can call that arc, what was it? Should we just call this Y? We already have X, so let's do that. Plus whatever the length A, Y, B is, and that is a arc length. And that arc length is created from this radius here. So what we're going to do is use r theta. R is r, which we don't know. So yeah, we're going to have to work out what that is. R is going to be equal to 2 squared plus 6 squared, all square rooted. So that is going to be 12 plus r, and theta was 2.498. Okay, so now r is equal to square root. It was 2 squared plus 6 squared. I'm really hoping it was, 2 squared plus 6 squared. So let's do that. So that's going to be square root 40, which we can't really work out, but yeah, we can make it 2 root 10, but there's no point. So this is 12 plus square root 40 times 2.498. So all we need to do is work out what that value is. So let's get to it. So 12 plus 2.498 times root 40. Again, it doesn't matter if we're in radian mode or not. So 27.8, let's call it. And that should be in centimeters. Cool. Bit tricky, but not too bad, hopefully. And then find the area of the shaded region. Well, we're going to obviously be using half r squared theta. Or just the... so if we use half r squared theta, that will give us this kind of semicircle bit, but it also gives us this triangle. So we need to minus 2 angles of the triangle, which is a bit annoying, but should be fine. So we're going to also minus XAB, let's call it. So we're going to use half r squared theta minus XAB. So let's work that out. So a half, we worked out what the radius was. It was root 40. So a half root 40. And then the angle was 2.498. And we're minusing XAB. And XAB is going to be a half times 2 times 12. And let's do it. Half times 2 times 12. So basically just start minusing 12. And if you do subtract these, you're going to get a hopefully satisfying result. So 0.5. I don't have numlock on, 0.5. Square root 40. Oops, there we are. Times 2.498. Minus, again, I know it's going to be 12, so I'm just going to minus 12. What's happened here? Interesting. Let's try this one more time. So a half times root 40. That's what's happened. This needs to be squared. Perfect. Yeah, there's no way of recovering that. Half times 40, we can just call it instead, because we know it's going to be squared. 2.498, and then again minus 12. There we are. 37.96. Let's call it 38.0 to 3 significant figures. And again, that should be in centimetres squared. Okay, we have one last question, and then we'll be finished with this topic, so it's pretty tiring. Yeah, this looks fun. So we have a big Z angle, so right away, just because I've seen it, I'm just going to put the theta there. Okay. And in the diagram, AOB is a quarter circle. So this whole thing here is a quarter of a circle with centre O and radius R. The point C lies on the arc AB, and the point D lies on OB. The line CD is parallel to AO, and the angle AOC is theta radians. So it's the perimeter of the shaded region in terms of R, theta, and pi. So we want basically this length, and the arc length. Okie dokie, let's get started, shall we? So this length CD, that should be okay, because this is the adjacent to this side. So we're going to be using cos, so we can say cos theta equals adjacent over hypotenuse, so that's going to be, let's call it CD, that should be a D, not a P, over R. So part of this is going to be R cosine theta. Not bad. So we also know that this total length is going to be R as well. But we want to get rid of this little chunky bit here. That's the opposite side. So that's going to be essentially the same thing. So OD is going to be R sine theta, right? Because it's basically the same thing. And then all we need to do is work out that little part of the area. So how best to do this? So if you think about how to work out the kind of area of this, what we can do is we can say that this part of the angle here, right, is 90 degrees, which if we're talking about radians is a half pi minus theta, right? And that will give us a little sector, which we can then use. Or not a sector, we actually want the arc length, so SR theta. Okay, so our total perimeter is going to be R cos theta, nice and easy, plus, and then we need to do R minus R sine theta, and then we're going to plus, and again, remember that that sector is going to be S equals R theta, so that's going to be a half, actually no, let's do it the other way, R times a half pi minus theta. So that's going to be plus R times a half pi minus theta. That is going to be our expression. It's an ugly one. It's a real hideous one, but not too bad, hopefully. And hopefully you see where everything comes from. So just to go over again, the perimeter of the shaded region is CD, DB, and CB. Right, to work out that was trivial, and then this one we had to do R minus the length OD, which was the sine theta part, and then we had to work out the arc length. So the only way to do that is to have this line here, so that angle was half pi minus theta. Bit of a pain, not going to lie. And yeah, that's pretty good. And then part B, for the case where R is 5 and theta is 0.6, find the area of the shaded region. Yay! Okay. So what we can do is we can use area of a triangle, area of a sector minus the area of a triangle, right? So this is a big pizza slice, so we can take this minus the area of the triangle. So let's work that out. So what we're going to do is do the area of a sector, which is a half r squared theta. So I'm not going to sub in the values now. It's just like a little thing I do. I like to do the algebra first to make sure I'm okay. And then that's obviously going to be a half pi minus theta. And then subtract the area of the triangle. So the area of the triangle is going to be a half base times height. Good lord, that's going to be hideous, but let's get to it. It doesn't matter which way around the base is. Let's call CD the base because r cos theta, that's fine. Half r cos theta times the height, which was this bit, which was r sine theta. And now we're going to sub in r equals 5 and theta equals 0.6. So what I find is when people sub it in earlier, because you're going to get really ugly looking decimals, they can make mistakes quite easily, which is a shame. A half, so r squared, and then we have, I'm going to call it pi over 2 for now, minus 0.6, minus a half, 5, cos 0.6 times 5 sine 0.6. Good lord. Okay, so I might write this in a slightly different way on the calculator. So for example, 5 and 5, we can make that half 5 squared cos 0.6. Actually not, I'll do it fully just to just so I can suffer for you guys. So 0.5, I do draw the line at making fractions though, so I'm going to change a half to 0.5. 5 squared, open bracket. I know I said I don't like fractions, I just made one. That's kind of funny. Minus 0.6, whoops. Minus 0.5 times 5 cos 0.6 times 5, whoops, sine 0.6. Okay, good. Let's call that 6.31 and call it a day. And it's in centimetres, so centimetres squared, once again to 3 significant figures. And that is all we have today. So again, these questions are heinous, to be honest. They are fairly tricky, but again, if you keep your head screwed on a bit, no matter how ugly something looks, like this is the actual answer to this. You can look up the mark scheme if you want. It's ugly, right? So in terms of looks, you can't really judge your answers. What you have to do instead is actually kind of logically work through them and make sure that they make sense. But that is it for this topic, and I hope to see you in the next one.